The last video, dear students, I was discussing about the instrumentation part of the visible spectrophotometer. So here the light source is going to be usually used is deuterium or hydrogen lamp, which gives 180 to 350 nanometers of electromagnetic radiation, which falls into the UV range, and xenon arc lamp, which is people earlier used it also as a source for UV radiations but found to be not so stable. Then they went for, so they are going to use the other kind of lamp source that is visible for visible radiation, that is tungsten lamp is being used, which gives an wavelength of 350 to 2500 nanometers, wherein all of us know that it is going to be up to 800 nanometers, which actually be used for the visible radiation. Followed by the source, there will be a wavelength selector which is being used. It's also called as a monochromator, because here we are supposed to get a particular wavelength of light to be interacted with the molecule and study the particular substance, as the light which is coming out of the source is not exactly of a particular range of means it doesn't falls into a small range of electromagnetic radiation, but instead it's going to be of complete stretch of nanometers, of hundreds of nanometers of range of radiation is going to be coming through. So therefore people are going to use different kind of wavelength selectors based on the requirement. For example, filters, people are using it, which are going to be very simple source or simple wavelength selectors which absorbs the light for all the regions except for one. People are using gelatin filters, where they are using gelatin plus organic dye, which is going to be placed between the glass plates, and based on the color of the plate, the light, the other wavelengths are going to be get absorbed. So this particular type of filters are going to be used, gives about 40 nanometers width of wavelength of electromagnetic radiation. That means the light which passes out of these particular filters will be fall into 40 nanometers, not just means within a range of 40 nanometers. For example, we have used these kind of filters in calorimeter, which we have commonly using in the labs. Then we come across with other kind of monochromators, which are used to get mono means single, chromo means color. So what people are using is they are using prisms, and these particular prisms are going to give the light of a little more specific range of wavelengths, which is with a little more shorter number of wavelengths lights. So it depends upon the apical angle and material used. These particular prisms are going to give, and the light which comes out of the prism are going to fall into different ranges. So they are using Carnot quartz prism, which is having 60 apical angle, 60 degree. There is little prism which is having 30 degree as a apical angle. So for visible radiation, generally people use the prisms of normal glass, but in case when we want to use UV radiation, then it's always suggested to use silica quartz or fused silica, because the glass, normal gas, is going to get heat up when visible UV radiation falls into it. Then sample holder, again people are using glass in case of visible, whereas quartz is being preferred to be used in the UV. As I told you, the glass is going to be absorbing the radiation, and followed by that it gets heated up, and there is a chance that during the process of study it may broke down if it is UV used. Then there are a number of type of detectors from the sample holder. Now the light will actually get passed through the detectors. There are varieties of detectors people are using. First is photovoltaic cells. They are very simple type of detectors. So where photovoltaic cells is made is named based on converting the solar energy, because photo into a direct current, voltaic. So here construction, you can see there down there will be two electrodes. In between that there will be the photo material which is going to be applied on, and which is having N and P type of silicons. So when the light falls onto this particular negative electrode side, so then automatically the electrons are going to get released, and these electrons are going to involve in the passage of current. And based on the amount of light which falls, the number of electrons are going to vary. At the same time, the amount of current which is going to get passed through the circuit will also vary. So this is how the light which is being passed through the sample is going to be detected by photovoltaic cells. The most widely used type of detector it is. And why? Because the cost wise it's very less, and working wise it's very simple one. Next is phototubes. Phototubes is also called as photo multiplier tubes, also some people call. The phototubes are going to be the one which is having a structure like this. You can see there where the light is going to be allowed to pass through. It's going to be consisting of a glass wall through which the light can pass through, and it falls onto an anode, which is actually a curved sheet of light sensitive material will be applied onto this. So when the light hits, it's going to eject electrons, which is going to be carried out by the electron which falls onto the anode, and then there will be generation of the current. And these particular phototubes are being used together in number of means in order to give more specificity and in order to amplify more number of signal. People are using it multiple times, so that more number of it can enhance the signal to a larger extent. You can see down there. So there will be number of diodes which are going to be kept at around 40-degree angle to each other, 40-45 degree angle to each other, so that whatever the electrons ejected from one diode is going to hit onto the second, which ejects to, like that there will be multiplication of the electrons. At the end there will be large amount of electrons is going to get ejected out, which goes into the reader, so that a more amount of, means very small amount of signal can also be able to be observed and can be detected through this particular one. It has a lot of usage in terms of its ability to amplify a small signal also, and it can get noted a unnotable signal in normal kind of detector can also be get noted by the multiplier tubes. Then we come across with a different type of spectrophotometer, which is little altered than that of the first one. So here people are using it as a double beam spectrophotometer. Double beam means here the whatever the light comes out of the source through the monochromator is going to be made to supply, the light is going to be divided by a divider, and this divider is going to be continuously rotating so that it alternatively sends the light through the reference cells as well as through the sample cells, and there will be very small difference in terms of time, so together these lights are going to get up are going to be almost coming out of the sample, and the reference will go fall onto the detector, so that simultaneously whatever the reference value is there will be nullified from the sample value, and we can able to get the amplification of exactly only the absorbance which is happening by the molecules present within the sample cells. So that is what actually happens with the double beam. This is the again the spectrophotometer, which is how it's going to be working with a very simple constructions here is shown here. So people in monochromators, they are also using graters. Graters are nothing but they are small scale like structures which is going to have number of etched structures which can give the light of a particular single wavelength itself. And if you can come to the applications of UV visible spectrophotometer, so UV visible spectroscopy is very widely used in qualitative and quantitative analysis. So qualitative analysis, because many of these organic compounds, they have a very characteristic absorption maxima, which is going to be used in order to understand what type of a molecule is present in the sample. Because for example, if we say protein has an absorption maxima of 280 nanometers. So if protein is present within the sample, we can able to understand, means we can able to determine it. Similarly, the DNA or nucleic acids, which is going to be have 260 nanometers, and there is this kind of qualitative analysis is going to be possible, like 340 for NAD, 340, like mean there's so many molecules are there having a particular range of their absorption maximas. Then it is also going to be used as a quantitative, because as we know, by the formula of A is equal to epsilon BC, C can be calculated uh, by knowing the molar absorption coefficient as well as the OD value. We can calculate the concentration. People also do it by using a very simple method of using standard curve, which generally we are going to be employing in the normal practical classes. Then we can also use this particular method for detecting the impurities. Detection of impurities, because again all the organic molecules, as I told you, have a specific absorption coefficient, and presence and absence of impurities are going to be affect their absorption maxima as well as the OD of absorption. So this change in the absorption maxima or OD in absorption can give us an idea about type of impurities present in the organic molecules. Then we come across it, detection of isomers are also possible with this, because the isomers are going to be having a different wavelengths of absorption, then can be easily detected. Then determination of molecular weight also is done by using Beer's law. So you can see some of the absorption maxima. So you can see there, like GMP to 50 5 nanometers, CMP to 71. So all these different nucleotide monophosphates have different absorption maxima, and some of the protein amino acids in protein also going to show absorptions, like tyrosine, tryptophan, mainly because of their intrinsic comfort due to their aromatic ring, the presence of double bonds. So specifically, if you come to the absorption of a spectrum of biomolecules, so in case of biomolecules, if it is present with the polar solvent, in case of proteins, it shifts to the less polar, means the lambda max and extinction increases with shifting to the less polar solvent. Aromatic amino acids, means that it shows that aromatic amino acids are on surface. If the lambda is going to be higher than the free from, then it indicates that it is surrounded by non-polar substances. And lambda is always more in case of protonated amino acids if they are present on the surface. If the absorption changes as a function of pH, then we can say the negatively charged amino acids are present on the surface. And if absorption indicates widely different pKs, then amino acids is a strong polar environment is present on the surface. So like these aspects are going to be able to be understandable by knowing the absorption spectra of these biomolecules. Then structural analysis, like people are using this in understanding the DNA denaturation renaturation studies. So denaturation absorption increases at 260 nanometers. So that increase or decrease in absorption can able to tell us. And even people are using this particular one in understanding the solvent perturbation. Perturbation means here what happens is that when you change the solvent polarity, then automatically there will be change in the absorption. So it can, in case of protein, there will be bathochromic or hypsochromic effect. without changing the conformation. This phenomenon is called solvent perturbation and can be okay. So here there is some practically solvent like dimethyl sulfoxide, dioxane, glycerol, mannitol, sucrose. So these are all going to be found, means they are being used in solvent perturbation studies, uh, because they are miscible with water. This method is most commonly used in understanding the presence of means how many determine the number of aromatic amino acids present, and binding of small molecules to the protein can also be studied by this method. For example, lysosome. Lysozyme has four tryptophan amino acids on the surface. When substrate is added, the absorption spectrum is going to be get shifted to longer. In case of tryptophan, that shows uh, means the number of tryptophans got varied. So solvent perturbation indicates only three tryptophan on the surface. So this can give us an idea, and it concludes one of the tryptophan was present in the active site like this. Then quantitative, so based on the absorption maxima by using Lambert-Page law, we can able to do analysis of quantitative, and even we can construct a body of means measured body can be constructed into a standard graph and which can be used for assay. Then we come across with the enzyme assay. So rate of enzyme activity can be determined by either using a product appearance or disappearance or reactant disappearance. We can, which is going to cause a change in the absorption of radiation that can be used as a characteristic. For example, in case of lactose dehydrogenase, so NADH, which is going to involve in absorption of 340 nanometers, whereas NAD does not absorb at 340. So this can be used as a characteristic for understanding the enzyme assay. Sometimes if enzyme by itself is not involved with the substrate or its product, if it is not directly involved in absorption of radiations, so then people are going to use the enzyme activity by coupling the process with an other enzyme, wherein the product of the first enzyme reaction can be used as a substrate for second enzyme, where the product of second can involve in the absorption of radiation, and that can be calculated, and indirectly it can give us the idea of the enzyme activity of the first enzyme. Then people are using this method for molecular weight determinations also. So by using formula M is equal to AWB by OD, where A is molar extension coefficient, B path length, and W is the weight of the substance in grams uh, per liter. So it means we can use this particular formula and calculate the molecular weight of a substance also. And lastly, we come across with another and a little alterations within this particular spectroscopy, which can give us a different spectroscopy. So different spectroscopy is obtained by subtracting one absorption spectrum with another. So why exactly people go for different spectroscopy? Because so this gives more minute informations about the particular molecule or the substance which is being studied. So this particular and also it helps in nullifying the high background absorbance. So difference of the spectroscopy can be obtained in two ways. One, by subtracting the subtraction of one absolute absorption spectrum from the another, or by placing the sample in the reference cuvette and another in the test cuvette. Together we can pass it through a double beam and we can get a difference spectra. So difference spectra has three important features as compared to the normal one or absolute spectra. So difference may contain negative absorption values also. So absorption maxima or minima may be displayed, and extinction coefficients are going to be different for those peaks of absolute spectra, and there are points of zero absorbance also can be made in this particular case, and there is points are found to be in both the kind of species, molecules exhibit same identical absorptions. We call it as isobestic points. So these isobestic points are going to be very much useful in understanding the molecules. So this is all about the UV visible spectrophotometer or spectrometry. So in case of any doubts, please do feel to contact me. I'll help you out with the understanding it. And next we'll get into the another type of spectrophotometer. It can be, I think we'll go for IR.